Thank you, everyone. Can everybody hear me okay? All right. So I'm Ryan Sriver from the Department of Atmospheric Sciences at the University of Illinois, and I'll kind of give an update on some of the things that we've been doing following up on Don, using the Community Earth System model on blue waters, in particular to study or analyze the effect of hurricane-ocean interactions. And we've also been working on some visualization tools, so I've got a nice animation, hopefully, that will work here that we can show at the end. And this is in collaboration with Rob Cisneros and David Bach at NCSA, who work in the data analysis, something, I forget the group, at DAV or something for blue waters. And it's supported through an NCSA faculty fellowship program. Okay, so why do we care about tropical cyclones or extreme events? It's because they pose serious risks, right? So hurricanes cause a lot of damage, cause a lot of flooding, economic and damage to natural and human systems, in the tens of billions of dollars range. So understanding these extremes, and particularly the interactions between the occurrence of these extremes and changes in climate, are extremely important because extremes drive economic impacts. So when we talk about climate change and we say, well, it might be 2 degrees warmer in 100 years, what does that really mean, or what does that mean to people? Right? What matters to people are how the distributions of extreme events or storms or something that's more salient and linked to natural and human systems. So the big question is then, this is from Time a few years ago, is are we making hurricanes worse, right? Or how are hurricanes changing, or how is the variability or the tracks, the intensities, the occurrence of these storms changing kind of under global warming? And this is a complicated question because in part we don't really understand even how tropical cyclones interact with the climate system at a very basic fundamental level. And that's where we come in, is we're trying to understand or quantify what is this relationship, right? Do tropical cyclones or hurricanes just passively respond to changes in the climate, or are they active contributors to the climate change or to the climate system? And one way we can look at this is looking at the effect of hurricanes or tropical cyclones on the upper ocean. Here's a hurricane from 20 years ago, or 18 years ago, I guess. And showing here this cold wake, right? So the black line is the track of the storm. This blue area is these cold surface temperatures that are left behind the storm when it passes by. And this cold wake is produced primarily through vertical mixing. So the ocean is stably stratified. You have warm water on top of cold water. And as these storms come through, they vigorously mix the ocean. They bring this cold water to the surface. And this is shown here through a vertical profile of ocean temperature before and after the storm. Black line is before the storm, right? You can see warm surface water, this thermocline where you get a strong temperature gradient, then colder water below. Then after the storm passes, right, it tends to deepen the mixed layer, right? It brings it cools the mixed layer, deepens the mixed layer. The net result of this, if we look at post-storm minus pre-storm, is you get a cool surface, which we see here, and in addition, or in accompanying with this, is a warm anomaly where you have warm ocean temperatures or warm ocean waters being injected into the subsurface ocean, right? So this is this vertical mixing is kind of, you can think of it as an irreversible mixing of the ocean. It's raising the potential energy of the ocean. It's doing work on the ocean, right? And even though it's intermittent, storms are kind of weather events, they still impart a huge amount of energy into the ocean, right? This cold wake here is the size of Florida, right? This is a huge region. So what we're trying to understand is what happens to this heat? Once you inject heat into the subsurface ocean, where does it go? What happens to it? Is it important for the climate system, right? Ocean heat uptake is an important contribution to changing climate. So what we thought, or kind of taking a step back, is this is for one event. What if we looked at this on a global scale? So here's some observational analysis from a few years back where this is what we did. We just looked at all of the cold wakes or all of the kind of storms occurring over a 10-year period. And we just looked at the SST anomalies. How much cooling does the tropics experience due to the effect of tropical cyclones? And it's actually quite substantial on a year-to-year, on an annual basis. And what we can then do is say, okay, based on the amount of cooling, let's turn this into a mixing. Can we estimate the amount of vertical mixing or diffusivity experienced by the upper ocean due to the effect of these storms? And what we find is that this is pretty substantial too. In fact, it's large enough to account for kind of the missing mixing in climate models that are currently missing, that have to be parameterized in order to correctly simulate the global ocean heat budgets. Right? So the idea is perhaps these types of events, these transient weather extremes, are not being simulated by the current class of climate models. And as a result, perhaps they're missing these important kind of climate-sensitive sources of ocean mixing that can affect ocean heat and energy budgets. Right? So there's strong observational evidence for climate interactions that can influence ocean heat and energy budgets, but can we model this? Right? Can we model these processes? This is hard to do because there's an inherent trade-off between model realism and computational tractability. Right? So if, this computational trade-off is kind of shown here in this cartoon where I've got number of simulations or some sort of metric for a computational resource, number of simulations or core hours or something along the y-axis, then increasing model complexity along the x-axis. These blue ISO lines here represent lines of constant computational cost. Right? So if I have a given allocation on blue waters, what can I do with it? Right? I can take a simple model and run it lots and lots of times, looking at parametric uncertainties, looking at natural variability, looking at structural model uncertainties, looking at emissions uncertainties, whatever we want. Right? We can do uncertainty quantification, machine learning, all of these things. But we're sacrificing the model realism because we're using a simple model. Right? On the flip side of this, we can go to complex models or finer scale models like Don was showing. Right? But here now, because of the computational expense of these types of simulations, we can only run a very small number of them, right? Or we can't run them for very long. So we can't do uncertainty quantification. This is more like a best guess. Right? Here we're maybe in the realm of underconfidence because the models lack physical realism. Here we're perhaps overconfidence, where we're getting our best shot or our best guess at the answer, but we're not really sampling the full range of possible outcomes because we're not able to do robust uncertainty quantification. And then where we are, this high-resolution CESM stuff, is we're kind of out here on the fringe of this. We're kind of pushing the limits of the model complexity. So what are we actually doing? We're using high-resolution configurations of the Community Earth System model to look at the relationship between tropical cyclones, upper ocean, and the Earth's climate. So what is CESM? For people who may not be familiar with climate models, it's a numerical, deterministic global climate model simulating the physics, the dynamics, and interactions between the various components of the climate system, including the atmosphere, with or without chemistry, the ocean, again, with or without chemistry, the land surface, glaciers, and even polar land ice. I think the new versions of CESM have a dynamic land ice component. So what are we doing? We're running 3 multi-decadal pre-industrial control simulations using the 25-kilometer atmosphere. So we're using very high-resolution configurations of this model, global model. And we've got 3 different setups here, 3 different simulations. One that's uncoupled, where we specify the ocean conditions, right? So we're just cutting out any sort of ocean-atmosphere interactions. And then we have one that's partially coupled with a slab ocean, meaning that it captures the thermodynamics, but it lacks the dynamics, or it gets the fluxes but no transports. So you think of this as partially coupled. And then we have a fully coupled simulation with a 1-degree ocean general circulation model with full thermodynamics, full dynamics. So in terms of tropical cyclone research, this is where the field is mainly, right here, looking at uncoupled simulations with specified ocean temperatures. If you want to know how the tropical cyclones are going to change in the future, you change the SST patterns based on CMIP5 results or something like that, and then you run it through an atmosphere-only simulation. You see what tropical cyclones look like at these 25-kilometer scales. What we're doing is really kind of pushing the limits here by going to fully coupled, right? And we need blue waters to do this just because of the enormity of the computational expense. And both the resolution and coupling are important for looking at these connections, but they're computationally intensive and requires petascale or even exascale resources like blue waters. And here's kind of one example of the limitations that can arise due to the lack of resolution. Right, here's what a tropical cyclone might look like in a 25-kilometer atmosphere. This is what the ocean might see based on various levels of resolution or configurations of the ocean model. This is, of course, ocean model, finer scale ocean model. Right? So what I'm saying is, even though you're running a fully coupled model, if you don't have adequate resolution, this is what's going on in the atmosphere, but this might be what the ocean is seeing. Right? Why blue waters? Because CESM scales pretty well on blue waters to about 15,000 cores. The high-resolution versions of the model have been ported there already and tested on blue waters by people like Don's group and Susan Bates from NCAR, who will be speaking today. So we've kind of been piggybacking on what's already been done, using these versions of the model, updating them with some of our own particulars based on our objectives, looking at tropical cyclones, and kind of running with it. So the main challenges that we're finding is that when you go to fully coupled, we have to update the surface exchange parameterizations for high wind conditions. Right? So you have a lot of momentum exchange between the ocean and the atmosphere, but these climate models were never designed to capture extreme events. Right? We are now in the realm where we're simulating weather in global climate models. And these are models that were originally developed at, like, say, 4 degrees, 3 degrees, something like that. Now we're running them at scales of 25 kilometers. And these surface exchange parameterizations just are not capable of capturing these types of interactions, particularly for extremes. Archiving, output, saving output, these are big challenges because now, again, we're not looking at this from the perspective of 100 years of climate change, right? We're using long climate runs, but looking at weather. So we're saving hourly output, 4-hourly output, things like that. And also developing a reliable tracking algorithm. These storms form spontaneously out of the model. Right? How do we identify them, track them in the model? Current project status, we've got about 100 total simulation years, 30 years of each, so enough to get a climatology plus kind of 5-year spin up for each one. And we're looking at about 150 terabytes of output right now. So I'll just briefly go through some preliminary results, just kind of graphically. This is what the tropical cyclones look like in the model. Here's the observations distributions over a 30-year period. Here's 30 years of the atmosphere only, 30 years of the fully coupled. So you can see the patterns the patterns generally agree. The model does a pretty good job of capturing the global tropical cyclone activity. The atmosphere-only simulation tends to overestimate intensity. Fully coupled simulation tends to underestimate intensity. We'll speak about why that is in a moment. Looking a little deeper, here's just categorizing weak versus strong storms for the different simulations. The key thing here is blue is observations. These others are the model runs. So we see on an annual basis, we get about the right number of storms globally in terms of weak and strong. We also get a nice seasonal cycle in all of the basins. These are important checks because it means that the model is getting the storms right for the right reasons. Why does it matter? Why does coupling matter, or how does it affect tropical cyclone intensities? This is, I said that the intensity distribution is a little bit less in the fully coupled model, and the reason is because of these interactions, right? Here you've got, this is the evolution of surface wind kind of from the model, from the storm perspective in the uncoupled simulation, where you get here's kind of peak intensity, but here's the SST, right? SST doesn't change because it's specified. Here's the same plot for the coupled simulation, where now you see this negative feedback of SST which limits the intensification of these storms, right? You've got this interaction now where you get this cooling effect. Because of this vertical mixing, storms don't get as intense, surface fluxes don't get as strong. So my point here is that if we really want to understand, or if we want to simulate how tropical cyclones are changing under anthropogenic global warming, we need to be capturing these feedbacks rather than kind of missing them, right? Atmosphere-only simulations are missing these feedbacks. We're also doing some visualization. Once we have these huge simulations, how do we actually visualize or try to understand what we're looking at here? So this is, here, let me see if I can get this plot working. Black dots here are genesis points for tropical cyclones. What we'll see here is surface wind drag and temperature difference between an ocean-only simulation where we force the model with tropical cyclones, and then we have a simulation where we have no tropical cyclones. So we can look at the effect of the storms on the surface temperature. All right, let's see if we can get this going. This was created by David Bach and Rob Cisnero and my student Hui Li, which is very, very nice. So here you can see the cold wakes, right? The storms are occurring, cold wakes. But what's interesting here is you also see this warming, right? You can see warming here in the tropics. Right? These effects have kind of teleconnection effects, where the mixing is occurring kind of in a local scale, but then it has an important, or it has larger scale influence on the dynamics of the ocean. Here's a zoom in of some storms. The Western Pacific, storm wakes. Here you can see now this effect in the Kuroshiro current, the intensified western boundary current, right? The storms kind of, this advection of this heat that's being injected into the ocean by the storms. We're just looking at surface temperature here. Really, I mean, and hopefully at some point we'll be able to turn this into a 3D a rendering where we can actually look at the subsurface ocean as well, not just the surface. But anyway, this is very new, very kind of still work in progress. So, but I think it's pretty exciting. Conclusions, we're using high-resolution configurations of CESM, investigating relationship between tropical cyclones and climate. We're doing a multifaceted sensitivity experiment where we're running multiple simulations looking at the effect of coupling. We find that coupling significantly influences cyclone activity. The feedbacks are important for large-scale climate. And the results point to the importance of coupled interactions and understanding these climate-cyclone relationships. Finally, the next steps, we are now running a climate change ensemble, or a climate change experiment, where rather than pre-industrial control, now we ramp up CO2. How do the storms change under increased CO2 forcing? Also, atmosphere-only simulations where we can use SSTs from the coupled model, right? Because the storms occur spontaneously in the ocean, spontaneously in the model, we have no control. There's no way of pulling out the storms to see what the effect of adding the storms is in the model. So what we're going to do is say, okay, let's use the coupled model as the control, and then pull out the effects of the storms and run the atmosphere-only simulations where we use SSTs from the coupled model, but we pull out the cold wakes. Right now we can look at how does that affect the representation of tropical cyclones in the atmosphere-only simulation. And this will help us get to a better understanding of really what I'm most interested in is why do tropical cyclones even occur? Is there some fundamental importance of them for the tropical heat budgets or for the Earth system? And these types of kind of again, these types of simulations can really help us understand that. And then we're also doing some economic impact modeling, looking at landfalling events and things like that. And here's some papers led by a couple of my students, Hui Li and Andrew Huang, summarizing some of these recent simulations. Thank you.